Welcome to our lesson on work energy. Work is defined as applying a force through a distance. Therefore, if we're trying to calculate work, it's going to be force multiplied by distance or force multiplied by the change in our displacement. And the unit for work, well, since we're multiplying force, which is in newtons, and multiplying it with distance, which is in meters, we're going to get a new unit called joules. So joule is the work done when 1 newton of forces moves an object 1 meter. And we're going to write joules with just the letter J. So let's do an example to calculate work. A force of 30 newtons is applied to accelerate an object from rest to 10 meters per second in 6 seconds. What quantity of work is done? We are given the force, and we don't have the distance or displacement, but we do have enough information to find it. And this information right here is related to kinematics, so we are going to use one of our kinematics equations to solve for distance. Okay, so the first thing I'm going to do then is find d. We are given vi, vf, and t. And we're looking for d. So the equation I'm going to use is d is equal to vi plus vf over 2 multiplied by our time, because I'm looking for distance. So vi is just 0, vf is 10, and time is 6. So this calculation is going to give us 30 meters for our distance. Now we're going to find work. And work is force multiplied by distance. Our force was given to us in the original question, which is 30 newtons. And we just found the distance, it's 30 meters. So your final answer for work is going to be 900 joules, or you can write this in scientific notation, 9 times 10 squared joules. Here's another example. A force of 55 newtons is applied to a 5 kilogram object for 5 seconds to accelerate it from rest. How much work was done? So we're given the force, we are also given a mass, and then some information related to kinematics. Because we're given the force and the mass, with that information, because force is equal to ma, we can find acceleration. And with that extra piece of information, we could use that to help us find distance because we have other pieces of information from kinematics. So the first thing I'm going to do is find A using the fact that F is equal to ma because we have force and we have a mass. And if I'm trying to rearrange to calculate that, it's going to be force divided by mass. Force is 55 newtons, mass is 5 kilograms, so our acceleration is 11 meters per second squared. The next thing I'm going to do then is try to find d, because we need that to find work. We now know that the acceleration is 11 meters per second squared, and we are given time as 5 seconds. We're given v initial, which is rest, and that's 0 meters per second. And I'm looking for d. The equation I'm going to use for kinematics equations is d equals v I t plus a half a t squared. Since our v initial is 0, this term is gone. A is 11, t is 5. And then we're going to do this calculation and we're going to get 137.5 meters. The last thing we're going to do now is find work. Work is force multiplied by distance. Our force was given to us in the original question, which is 55 newtons, and the distance we just found is 137.5 meters. Our final answer is 7,562.5 joules. The next thing we're going to look at is multiplying two vectors together. Both force and displacement are vectors, and because of this, we cannot directly multiply them together unless they are in the same directions. When they are not, we have to count for the difference in direction, and this is done using a dot product. To simplify what's just being said here, what we're going to do is evaluate our vectors in its x and y components. So force can have an x and y component, and so can displacement because they are both vectors. Well, we know that work is force multiplied by the change in displacement or the distance. So if I want to evaluate this into its x and y components, we could have work in the x direction calculated from the x direction of a force multiplied by our distance. And we can get work in the y direction from our force in the y direction multiplied by our distance. The other scenario we can have is our work in the x direction if we're just given a force and we have some sort of x direction to our displacement. And the same thing in our y direction. When this occurs, we do need to change it into its components by using sine or cos theta. So we could use, instead of dx, d cos theta. Instead of dy, we could use d sine theta. And same thing for our force in this x and y components as well. So really, we are still going to use this for the most part, but we can break it down into its x and y components. So here's an example of that. A force of 25 newtons is exerted on the handle of a wagon at an angle of 35 degrees to the horizontal. If the wagon moves at 75 meters, how much work is being done? I'm going to draw a diagram first. Here's the wagon and its handle. We know this handle has a force being exerted on it at 25 newtons, and this handle is also on an angle of 35 degrees. We also know this wagon is moving, and it moves 75 meters. The first thing we're going to do is maybe break down our force into its x and y components, because we can see that since it's on an angle, we can have a force in the x direction and a force in the y direction. So I'm going to just look at this force over here. And we learned this before, that if I want to find force in the x direction, this is going to be 25 cos 35 degrees by using trigonometry. And in the y direction, this is 25 sine 35 degrees. So then when I'm calculating work, we're going to have a work in the x direction and the work in the y direction as well. So Wx is going to be Fx multiplied by our distance in the x direction. And for Fy is going to be Fy multiplied by our distance in the y direction. So for Fx, that's 25 cos 35, which is 20 newtons. And our distance in the x direction, our wagon is traveling 75 meters along the horizontal, or along the floor. This is going to give us 1,500 joules. Now looking at our work done in the y direction, 25 sine 35 for Fy is 14 newtons, multiplied by our displacement in the y direction. Well, this wagon is not going to float up in the air, nor is it going to sink it down to the earth. So our y direction is just going to be 0 since it's not moving up and down. This means there is 0 work being done on our wagon in the y direction. So then our final answer is just going to be the Wx. There is only one direction to worry about, and it was the horizontal direction. Our last part for work is finding work as an area underneath a curve. And we can do that under a force versus distance curve. So I'm going to draw an example here on the side, and I need you to copy this down. So here is our force versus distance curve. If we want to find work, we know that work is force multiplied by distance. And we can find this if we look at the area underneath the curve. I drew a dotted line because I'm going to break our shape down into two parts as an area 1 and area 2. So work is then going to be area 1 plus area 2. Area 1 is a triangle, area 2 is also a triangle. So we just need base and height and then divide it by 2. So our base is along the x-axis, which has a distance of 2. Our height is 3. So 2 times 3 divided by 2 will give us the area of that triangle. And then we're going to do the same thing for area 2. And the base is 2. The height is 3. And if we want to find an area of a triangle, we multiply base height and divide it by 2. So that's 6 over 2 plus 6 over 2, which is 3 plus 3. So that's 3 plus 3, which is 6 joules. Now we're going to try this again. F may be applied either as a positive or a negative quantity. So here's another graph that we are going to look at. Okay, so here's our graph, and we want to find work, which is the area underneath the curve. There are 3 areas we can consider. This can be the first area. This is the second area, and this is the third area. Note that in the third area, it is going to be a negative area because it's underneath the x-axis. So for our first area, we have a rectangle along the x-axis. This is 2 multiplied by our height, which is 3. So that's area 1. Area 2 is 1 times 1. Our base has a length of 1 and our height is 1 for that square. And then our last area has a base of 1 and a height of -3. Now we're going to simplify this. So that's 6 plus 1 plus negative 3. 6 plus 1 minus 3 is 5. So our final answer is 5 joules for the work being done described by this